Programmable features are those items that can be enabled or disabled or turned off and on using Insight. Quantum engines can be calibrated with an optional engine protection feature that monitors critical engine temperatures, fluid levels, and pressures. The engine protection feature records separate fault codes when an out-of-range condition is found for any of the engine protection sensors. The engine protection feature will then light the engine protection lamp. An engine protection condition is determined either based on the severity of the reading or the duration of a reading. A severity-based out-of-range condition compares the current reading to a predetermined threshold or range. The parameter is out of range when it exceeds this threshold. A duration-based out-of-range condition initiates engine protection when a predefined condition exists for a predetermined time. The derate mode of engine protection can impose a gradual speed or torque derate depending on the severity or the duration of the observed condition. With either derate, when the parameter first goes out of range, a 5-second confirmation period is begun. If after the 5-second period the parameter is back in range, no derate occurs. However, if after the 5-second period the parameter is still out of range, the condition is confirmed and the derate becomes active. An active derate causes the appropriate fault code to be logged, may light one of the diagnostic lamps, and applies a derate according to the table stored in the ECM. Engine protection is based on coolant temperature, coolant level, intake manifold temperature, oil pressure, OEM temperature, OEM pressure, coolant pressure, the crankcase blow-by pressure, and fuel temperature. The engine protection lamp in the cab flashes for 30 seconds prior to shutdown to alert the operator. If at any time during the warning period the parameter goes back into range, the lamp is turned off and the shutdown is aborted. However, if the parameter is still out of range at the end of the 30-second period, the engine will shut down. After any engine shutdown, the reason for the shutdown should be determined and corrected before continuing operation. The ignition key must be turned off for several seconds before attempting to restart the engine. A cool-down period is recommended prior to restarting the engine after a shutdown. When the engine protection shutdown feature is disabled, an engine protection fault does not shut down the engine. However, disabling the engine protection shutdown feature will not prevent the engine protection system from derating the engine as necessary. After an engine protection shutdown, the engine can be cleared for restart by the fault changing from active to inactive, calibration, or in some cases, a predetermined time delay. An intermediate speed switch can be mounted on a cab panel for operator access. A 3-position switch can be used if 2 intermediate speeds are desired with ISC validation. When ISC speed 3 is required, ISC validation cannot be used. This 3-position switch cannot be used to activate all 3 ISC speeds. Systems using 3 ISC speeds require an additional switch or switches. If a remote throttle is required, ISC 2 cannot be used. If a remote throttle is not required, a potentiometer can be used to obtain an additional 5 ISC speeds. These speeds are obtained as the potentiometer is cycled through the range. The ECM control system attempts to maintain the engine speed as long as the intermediate speed on-off switch is in the on position. The preset speed can be adjusted with an increment-decrement switch. When the remote throttle switch is toggled to the on position, the ECM receives a signal to switch engine control input from the cab accelerator to the remote throttle. For the ECM to switch the signal it uses to control the engine to the remote throttle when the remote throttle switch is moved to the on position, the remote throttle must be requesting less fuel than the cab accelerator, and there must not be a remote throttle fault. The ECM then controls the engine speed based on the signal from the remote throttle, and the cab accelerator signal is ignored. The ECM uses the input from the remote throttle to control engine speed until the remote throttle switch is moved to the off position, and the requested primary accelerator is less than or equal to the requested remote throttle. It is beneficial to limit engine speed and torque after startup until sufficient oil pressure is available to supply oil to the engine components. Under certain operating conditions, not allowing the engine time to develop oil pressure before accelerating can damage key components, especially the turbocharger. The maintenance monitor feature flashes to indicate to the operator that the predetermined interval is approaching. When the maintenance monitor reaches its predetermined level, the ECM flashes the lamp after each key on until the maintenance monitor has been reset. With the automotive or min-max governor, engine speed between idle and maximum RPM is determined by the accelerator position sensor input, as well as by the load applied to the engine. Since the accelerator position determines the amount of available engine torque, engine speed is directly related to the amount of load placed on the engine. An automotive governor requires more operator interaction to maintain speed, providing improved feel. An all-speed or variable speed governor provides aggressive speed holding capability, and small changes in accelerator position result in large gains in torque. This type of governor attempts to maintain a constant engine speed for a given accelerator position. The all-speed governing mode varies engine speed based solely on input from the accelerator position sensor. This governor attempts to hold engine speed constant when the accelerator is held in any position between minimum and maximum RPM and engine load is varying. Switch position 1 is enabled by default. This feature allows a change in the drop in engine speed when the engine is operating between the governor speed and the high idle speed. With this feature, the ECM can inject ether into the intake manifold while cranking if the engine is below a calibrated minimum coolant temperature or intake manifold temperature. The ether will continue to inject until a calibrated maximum engine speed has been reached. Two types of ether injection systems are typically used. The measured shot system cycles ether injection on and off, each cycle lasting a calibrated period of time. This provides a measured shot of ether each time the sequence is completed. The constant on system provides a constant supply of ether, controlled through an orifice. With this feature, the ECM calculates the amount of ether left in a given canister and logs a fault when the canister is empty. The fan clutch sensor inputs include the coolant temperature, intake manifold temperature, fuel temperature, OEM pressure, OEM temperature, and fan clutch switch. With the engine stopped and the key switch on, the operator cycles the accelerator 3 times to enter the diagnostic mode. Once in diagnostic mode, each additional cycling of the accelerator increments to the next fault code. If there are accelerator errors, this feature will automatically enter diagnostic mode when the engine is stopped and the key switch is on. Selecting delta for this parameter causes the commanded accelerator to be the difference between the primary accelerator and the deceleration throttle. With this selection, the engine speed begins to decrease as soon as the deceleration throttle begins to be depressed. Selecting minimum for this parameter causes the commanded accelerator to be the lower of the accelerator input from the primary accelerator and the deceleration throttle. With this selection, the engine will not begin to decelerate until the requested fueling from the deceleration throttle reaches the level of the primary accelerator. An engine is considered hot when the hot shutdown load percent of the engine is above the threshold set in Insight. The hot shutdown load percent is based on the duty cycle load factor, which is determined from engine fueling levels. This value is expressed as a percentage per second. This allows the rate of change in fan speed to help prevent belt hopping and slippage to improve drive belt life. The auxiliary speed governor is an application-specific feature that allows the engine to be governed by either an auxiliary speed or pressure signal. The feature uses a manual switch input to turn the governor operation on or off. It is often desirable to allow the engine speed to gently decrease with the application of a load to enhance drivability. This prevents jerkiness and protects mechanical components attached to the drivetrain from damage due to sudden applications of torque from an engine that is aggressively attempting to maintain its commanded speed. For these reasons, Quantum uses variable droop in the governor algorithm, where droop is defined as the difference between the no-load commanded speed and the full load commanded speed divided by breakpoint speed. The ECM calculates the proportional amount of droop at engine speeds between high and low idle. If the alternate idle startup feature has not been enabled in the calibration, the engine operates using the normal idle speed until the alternate idle switch is moved from normal to alternate. If the alternate idle startup feature has been enabled, the position of the alternate idle switch determines the idle speed at startup. The alternate droop feature allows the droop characteristics to be changed for high engine governed speeds and for the all-speed governor. Less governor droop provides a more responsive governor for more precise engine control. More governor droop provides smoother shifting and smoother mechanical clutch engagement. Each alternate droop setting provides the ability to select the high-speed governor breakpoint speed, droop percent, and the isochronous breakpoint speed. Droop percent at minimum and maximum throttle for the all-speed governor is also adjustable. The breakpoint speed determines the position on the engine torque curve where the high-speed governor will start to limit engine torque output. One of the switch inputs can be used as a validation input. In this case, intermediate speed control requests are not recognized unless the validation input is on and the ISC switch input has transitioned from off to on. With validation selected, 2 switch-activated ISC speeds are available. To switch to any of the other settings, the switch is moved to the position corresponding to the desired speed. With the automatic mode, the filter or oil change interval is determined by the maintenance interval value in fuel burned established by the calibration or by the number of hours of engine operation. With the manual mode, the maintenance interval is determined by tracking engine operating time. The maintenance monitor notifies the operator when the first of these factors reaches the predetermined level. When this monitor is used for oil change intervals, interval factor parameter is the expected life of the oil and filter combination, expressed in liters of fuel burned. This parameter is derived from type of oil used and the vehicle kilometers per liter. Refer to the service literature when selecting the appropriate interval factor for the application: severe duty, normal duty, or light duty. However, these intervals can be extended if a synthetic blend oil, such as Premium Blue 2000, is used. Refer to the product literature to determine how much the drain interval can be extended. The actuator electrical diagnostic feature provides diagnostics of the pulse width modulated driver circuits from the ECM. If an open or short circuit is detected, a fault code activates to alert the operator of the problem. Actuator circuit diagnostics are performed continuously whenever the key switch is turned to the on position. Diagnostics are based on the difference between the commanded PWM current and the feedback current. A short circuit fault is recorded when the feedback current is higher than expected and sustained for a period of time. An open circuit fault is recorded when the feedback current is lower than expected and sustained for a period of time. The fuel shutoff valve engagement delay feature slows the opening of the fuel shutoff valve during warm engine starts. The coolant temperature is used to determine when this feature delays the opening of the shutoff valve. With a warm engine, the fuel shutoff valve is not opened until the engine speed is above the threshold for a calibrated amount of time. This allows the fuel pressures in the timing and rail passages to become stabilized for improved fueling control, which reduces engine noise during hot engine starts. With a stuck open fuel shutoff valve, the fuel actuator shuts off the supply of fuel to the engine at shutdown. However, if the metering rail actuator should also become stuck, the ECM may not be able to shut down the engine. The Cummins system has built-in diagnostic capability, which alerts the operator of a system problem while the engine is running by illuminating one of the 3 diagnostic lamps. The yellow warning lamp illuminates to indicate a fault condition that allows the engine to continue to be operated. With this type of fault, the engine can still be operated but may lose some system features, which can result in power loss. This fault should be repaired as soon as it is convenient to do so. The red stop lamp illuminates to indicate a fault condition that can disable the engine. Operation of the engine should be stopped as soon as possible. The engine protection lamp illuminates when an out-of-range condition occurs. If the engine protection system lamp illuminates during engine operation, this indicates that a fault code has been recorded. The lamp will remain on as long as the fault is active. If shutdown is enabled, the lamp flashes to indicate an approaching engine shutdown. When this type of fault remains active, the engine power and/or engine speed will be gradually reduced. If the engine protection shutdown feature is enabled in the calibration, the engine will shut down after a short time delay to prevent engine damage. If the engine is not equipped with Sense, the following method can be used to flash out active fault codes. Turn the vehicle key switch to the off position. Turn the diagnostic switch to the on position. Turn the vehicle key switch to the on position, but do not start the engine. If no active faults are recorded, all 3 of the lamps will illuminate and stay on. If active fault codes are recorded, all 3 lights come on momentarily. Then, the yellow warning light and the red stop light will begin to flash out the first active fault code. First, the yellow light will flash, followed by a short delay. Then, the red stop lamp will flash out the first digit of the 3-digit fault code. After a 1-second delay, the red lamp flashes out the second digit. Then, after another 1-second delay, the red lamp flashes out the third or last digit. After flashing out the fault code, the yellow light will flash again, and the same fault code will flash out again. To advance to the next active fault code, move the increment-decrement switch to the plus position and then release it. The increment-decrement switch can also be used to return to the previous fault code. After reaching the final active fault code, moving the increment-decrement switch to the plus position begins the entire sequence over again, starting with the first fault code displayed. Sense engines are not equipped with a diagnostic switch. Active fault codes flash out when the key switch is in the on position with the engine not running. Quantum faults are flashed out first on the red stop lamp, and then sense faults are flashed out on the yellow warning lamp. Beginning with the first active quantum fault, the red lamp will flash out the first digit of the 3-digit fault code. After a 1-second delay, the red lamp flashes out the second digit. Then, after another 1-second delay, the red lamp flashes out the last digit. After the last digit, there is a 2-second delay, and then the next active quantum fault is flashed out. After completing all of the active quantum faults, the sense faults flash out on the yellow warning lamp. When all of the faults have been displayed, there will be a 3-second delay, after which the flash-out sequence begins again with the first active quantum fault code. The data link is activated whenever the key switch is in the on position, regardless of whether or not the engine is running. With the current QSK 45 and 60 engines, the J1587 data link is used by Cummins service tools. In addition, the data link provides information, formatted according to the SAE J1939 standard, to additional data logging equipment, such as electronic dashboards or other equipment's ECMs. At times, it is desirable to limit the engine torque output to protect the equipment, transmission, or change the functional characteristics of the equipment during a particular operating mode. The alternate torque curve feature provides the ability to switch between the 100% torque curve and two additional curves through the use of an OEM-installed 2- or 3-position switch. The dedicated PWM output feature allows the OEM to create a 12-volt pulse-width modulated signal whose duty cycle is selected by the calibration to be proportional to either engine speed, engine torque, or accelerator percent. The intended use of the analog signal is to control an engine or transmission that relies on an analog signal input. The dual outputs based on sensed parameters feature allows for two separate and independent 24-volt outputs to be turned off and on based on input values from 13 specified parameters. These outputs could be used to activate devices such as a fan clutch, audible alarm, or lamps. The 13 parameters that can be configured as inputs to this algorithm are engine speed, final fueling, boost pressure, auxiliary speed, oil pressure, coolant temperature, fuel temperature, commanded throttle, OEM sensor, OEM switch, ISC status, OEM temperature, and OEM pressure. Depending on the calibration design, all of the parameters or any combination of the parameters may be configured as inputs. The outputs may be turned on when all of the inputs become active or when any one input becomes active. The frequency throttle feature converts a filtered throttle frequency input into a requested throttle percentage. This feature applies to industrial and marine applications where a position or logic signal is not appropriate. The remote throttle can also be used in addition to a frequency throttle. Multiple unit synchronization allows two or more engines to be operated at the same speed, torque, or with commanded throttle input. Some of the parameters that apply to engine synchronization can be monitored. In a hard-coupled synchronization application, the primary engine sends a throttle signal to the first secondary engine. This engine passes the throttle signal to the next engine. This pattern continues until the last secondary engine passes the signal back to the primary engine. The feedback duty cycle to the primary engine is compared with the output duty cycle from the primary engine. If this comparison is outside of a calibratable range, a fault condition exists and the engines will be shut down. The output signal from each engine is generated on the PWM out pin of the OEM harness. This output is then the input signal for the next engine on the VSS input pin of the OEM harness. The last secondary engine provides this as a feedback signal on the VSS input of the primary engine. In a soft-coupled application, the primary engine sends the throttle signal out to all of the secondary engines at the same time. This feature utilizes the dedicated PWM output feature to generate a throttle output duty cycle on the primary engine from commanded throttle input. This signal is sent to the secondary engine and read on the VSS input circuit. Since these engines are wired in parallel, if one engine stops, the others remain running. The soft-coupled marine application sends the throttle signal out to all the secondary engines through the J1939 data link. Since these engines are wired in parallel, if one engine stops, the others remain running. The ID pins configure each engine to operate either as the primary engine or one of 5 secondary engines. By using the pins, the need for a separate calibration for each engine is eliminated. In addition, for a service tool to communicate over the J1939 bus, it must be able to recognize which engine the information that it currently is receiving applies to. In some applications, it is desirable to provide the ability to continue equipment operation after an accelerator failure occurs. The accelerator limp home feature provides this capability. Accelerator failures are any out-of-range accelerator conditions. Idle validation is required to use the accelerator limp home feature. The industrial accelerator default feature determines the default accelerator values to be used when certain accelerator system errors become active. Depending on the fault condition, the accelerator value defaults to one of two calibratable values. The intent of this feature is to allow continued engine operation at sufficient power to maintain accessory loading. When this feature is enabled, it replaces the accelerator limp home feature. The overspeed protection feature monitors the engine speed and shuts off fuel to the engine if an overspeed condition is detected. The engine speed at which an overspeed condition is detected depends on the calibration. A fault is logged, and the ECM records engine data when the fault occurs. Fuel flow is restored to the engine when the engine speed drops below a secondary engine speed threshold.